Yes, so I'm going to be presenting on Bounce, which is an application that we've been developing at CFMS over the last 6 months or so, mostly focusing on the applications that we'll be doing, intending to use for this in non-destructive testing. So first, a little bit about who CFMS are. We're the Centre for Modelling and Simulation. We're an independent modelling and simulation company where we use cutting-edge technologies to design, model, and analyze complex challenges. So to do this, we rely on our high-performance compute resource in our on-site data center to solve both industry and government problems. So for example, in the aerospace industry, we develop models of testing processes to improve time and quality of test. As you might assume, this is quite relevant to this talk, but also we do work in rail, where we develop tools to optimize resource allocation to improve scheduling. And in manufacturing, we develop models of complex components like composites to improve development and performance. So briefly, what is non-destructive testing? So it refers to a process or a methodology which evaluates whether a component or structure or system is fit for service, particularly without causing damage or destruction. So a lot of the technologies that would be used for NDT are shared with medical diagnostics, so things like radiography or like X-ray testing, ultrasound, that kind of thing, to inspect the component. So in aerospace and energy, it's quite common for bespoke components to be produced. And in these cases, that safety is quite crucial. So a technician would have to have a good understanding of the current state of the quality of the component, so that the safety or the well-being of the user can be guaranteed. In construction or in infrastructure, on top of the safety considerations, you'd also have the complication that structures are usually expected to last multiple decades. So NDT is essential for extending the lifespan. And in manufacturing or even food production or that kind of thing, it's quite common that you'd have a high throughput of parts or things that require testing. So it's important to evaluate things quickly. So automation is quite useful. The challenges that we face are that many industries operate in a safety critical environment, as I discussed. So an operator has to have a high confidence that flaws which are introduced during production or in service will be found. This means that any technique that will be used to assess this has to be qualified. This is essentially just guaranteeing that it's capable of detecting a minimum flaw size normally that would have an impact on safety or operation. Usually this requires a lot of high fidelity data with genuinely defective components to ensure that that can be done. This is further compounded by the fact that data intensive processing techniques like statistical analysis or machine learning are being increasingly used these days. So large quantities of well-labeled data would be required to train machine learning models, for example, or else any output would have poor performance. Any kind of sentencing you might want to do wouldn't be very good quality. In reality, defects are actually quite rare. They don't occur all that often. So even when flaws can be identified, the labeling process can be the challenging step. So say that we found that a crack has formed in some component somewhere, working out the exact features like the length or the depth can be expensive and might require multiple techniques. And often a component will just be cut open so that it can be measured like directly, which basically means that the component has to be sacrificed. So it's difficult to get further data from it once you know what's in there. We're interested in generating synthetic data, so developing tools to do that, to improve the confidence in testing procedures, and also to provide input to things like machine learning. Specifically, we're targeting ultrasonic testing in this work. So normally that would mean you'd apply a piezoelectric transducer, which would vibrate to produce an elastic signal in the component, and then that would reflect from things like cracks or whatever it is that we're trying to find in the component. So why are we using MFEM? We have quite extensive experience working with finite element analysis in other domains. So we appreciate that it's quite a powerful tool in highly complicated problems that can be much harder to address using like a LTI system or that kind of thing. We've used Moose quite a lot in the past, but we've found that for this kind of work doing elastodynamics problems, it doesn't quite work for what we want. The reason why we like MFEM and why we're pursuing it for this is the integration with MPI, which allows it to be scaled to distributed memory HPC systems, so we can deploy it on our data center to run large simulations. And also compared to other FE tools, we appreciate that it's got quite good documentation and that it's an open source framework as well. So at this stage, we're mostly concerned with modeling propagation of elastic waves in complex materials, as well as interactions between these waves and floors. So we started off using the example 23 as the template, which is an implicit system for solving elastodynamic equations. We're interested in more of a dynamic system, so we're working towards implementing an explicit finite difference scheme, which solves this system of equations. So we're taking the mass, the damping, and the stiffness into account here, generating waves in the system using the force vector, and then stepping forwards in time using the finite difference scheme here. This is relatively straightforward. It's explained quite well in this paper if you're interested, so I'd point you there. We've integrated this into MFEM using bilinear forms, using these integrators to assemble the matrices, as we're targeting 2D and 3D simulation. And we began using the elasticity integrator that's built in, but have subsequently developed an anisotropic stiffness integrator, elasticity integrator, which computes the stiffness matrix from an arbitrary elasticity tensor so that you can do both isotropic and anisotropic materials using this application. We use Rayleigh damping, where we just take scalar multiples of the mass and the stiffness matrices, and then define additional material properties for the alpha and the beta term, but these are just scalar values. And then we use row sum lumping to simplify the matrices in the inversion process. And specifically, we're also using Neumann boundary conditions on surfaces, but we have Dirichlet also implemented, although we find that they're not that as widely useful. In terms of the workflow, I'll touch on this briefly. So Bounce is written to take a set of input files, which are specified up here. So we're using Gmesh to do the meshing and various other properties. But on top of this, we've built a set of Python tools to process the inputs, like the component geometry, the material properties, the floor geometry, loading properties, any outputs that you're interested in. We then use Gmesh to mesh the model, apply any absorbing layers or any other complicated or additional features that you might like in the model, and then ultimately write the outputs, then pass it into Bounce, do all of the setup, and then most of the work is done in this time stepping loop here. And then write if we want to, and then analysis we perform based on some external tools that we've written based on what it is that the user is interested in. So time versus displacement histories in X, Y, and Z can be analyzed using whatever your preferred scripting language is. We're using Python, or full field displacement in ParaView, built off of the implementations from MFEM. So digging into some of the applications that we're interested in doing, anisotropic materials are obviously quite an interesting one for us, as they're relevant in quite a lot of high performance materials that are used across a wide range of industries. The material properties are set from an elasticity tensor, So we've tested it for both isotropic and orthotropic materials. On the right here, I've just got a cantilever beam where we're showing on this plot here the percentage error in the displacement at each node, where we've got X, Y, and Z in blue, orange, and green, just to demonstrate that we're able to validate that it's doing the same thing under the same conditions. And then in terms of applications, two ones that are quite relevant just more generally is using titanium, which can be composed of individual metallic grains which have different orientation of the stiffness matrix. So we've got an example of a bit of an extreme example, I'll say here, of what scattering, the scattering of the ultrasonic wave looks like in this case, where I've just superposed the borders of the grain boundaries on here as well. But the hope here is that this demonstrates how challenging inspection can be in these materials and why this simulation tool is necessary. The second animation here just shows a wave propagating in a composite panel. So this has got a orthotropic elasticity tensor being used here in the structure of this second diagram here, where we've got fibers going in the X direction. And we can see as the animation progresses that there is quite a strong signal in that direction, which is exactly what you'd expect. We've also run very large scale simulations targeting developments in additive manufacturing, where the component geometry might be quite complex, as well as the material properties. So it's not always feasible to reduce the model in some way. So we're essentially required to model the full component. Element size in these kinds of simulations is driven by the ultrasonic wavelength, which is typically on the order of millimeters, and normally you would want several finite elements per wavelength. So if the part is on the order of meters, this isn't necessarily a trivial problem to solve. What we've done here is run a slightly larger model to demonstrate that we can run a 3D model, where I've got the geometry shown up here. It's close to 1 billion finite elements in this thing, where across a significant portion of our data center we're running at 2,000 cores, and it took just over 30 minutes to run 2,500 time steps. But it's a pretty reasonable amount of time for us to run the scale of model that we would be interested in doing. A specific application that we're interested in is acoustic emission. So this is essentially what happens in composites, specifically. Certain floors will release a pulse with some characteristic features, such as the frequency when a floor forms. Our goal here is to improve the ability to detect individual acoustic emission events, to diagnose the specific floor type that it might be associated with. These come from really small features in the geometry. So the way that we're currently modeling this is by applying a concentrated node directly to the individual degrees of freedom in the mesh, where the animation is just showing a demonstration of an excitation at different frequencies at different start times, at various different locations, just to demonstrate the capability here. There's a particular goal in machine learning. We want to increase the amount of data that we're generating that we could use to train models, as I mentioned at the start of the presentation. There's a few things that we can do to do this. So we can rely on the linear combination of individual signals to combine multiple events in the acoustic emission simulation to essentially replicate what we were seeing on the previous animation. But we could potentially combine arbitrary numbers of those from individual simulations. On top of that, we can use a broadband signal to measure the response from a wide range of frequencies, which is what this animation here is showing at the bottom. So what we typically would want to do to model an inspection is to couple a pulse into the geometry, which is what the top animation is showing, which might look like this. This might be the time time-dependent signal, which has this corresponding frequency spectrum. But if we apply an impulse, which has a broad band of frequencies, we can reconstruct the response from the top pretty much exactly. And in fact, we can do this for any frequency range that we'd be interested in examining from a single simulation. So essentially, by doing a single run, we can increase the amount of data that we get out of this by quite a significant amount, which would be useful for things like machine learning. Oh dear. Let's try that. Oh dear, one of the animations isn't loaded, sorry. The final thing that we're doing is to generate, we're trying to study the scattering behavior of complex floors. So I did have an animation here showing what it looks like when these waves scatter from these floors, but it seems like just the mesh is loaded. But typically the point is that this is difficult to do analytically to derive a set of equations. So finite element makes a lot of sense. Specifically, what we're aiming to do here is examine the mode conversion of the wave using the potential fields that we get from the built-in divergence and divergence and curl grid function coefficients to decompose into longitudinal or P waves and transverse or S waves, which we found works quite well for that purpose. To assess these potential fields. So what we want to do with this is combine this with the previous data generation methods to model floors independently of the rest of the model, which would again rapidly improve the amount of data that we can generate from different kinds of floors. This example here, this defect here is a little bit arbitrary, but I think it serves to show that scattering can be quite complicated from here, from even this sort of simple floor. So that's the end of this brief overview. So I'll just briefly summarize what we've been working on. So we've implemented an anisotropic elasticity integrator to assemble the stiffness matrix from an elasticity tensor, which we've currently demonstrated with isotropic and orthotropic materials. We've also implemented distributed loading via the inbuilt boundary projection tools to the grid functions, as well as implementing concentrated loads set directly to degrees of freedom. We've been able to look at individual wave modes, which mostly we've been applying that for generating large sets of data to study complex scattering behavior. So yeah, we think this has quite significant opportunities for data-intensive methodologies like machine learning, as well as things like sensitivity analysis and the optimization of designing one of these inspections. So this should have quite a significant impact on physical inspection and the qualification process. In terms of the work that we'll be doing subsequently, our goal is to simulate realistic ultrasonic scenarios. So it would probably be quite useful to implement arrays of individual transducers, as this is used quite widely across industry. And also a particular thing that we found is in using the divergence and the curl grid function coefficients. They seem to be quite slow at what we're doing. So potentially implementing an integrator would be quite a useful thing for us to do. If anybody has any advice on existing curl integrators that might be a good template, that would be good to hear from you. So that's it. Thank you very much for your time, and thank you for letting me present to you today.